Okay, so this is the first lesson on Unit 1920, derivatives of trig functions. So what we're going to cover today is, well, I'm going to cover box A, limiting values of trig functions. Yeah, that's done in the guide, so I'm not going to talk about it at all. Okay, so we're on to box B, derivatives of sine and cosine function. Okay. Now, at this point, we could do a derivation showing how, from first principles, we can derive the expressions for the derivative of the sine and the cosine functions. That's also done in the guide, so I'm not going to do it here. So in the red box here are the two facts that we need to know here. That if we have a function, y equals sine of x, and we want to take the derivative of y equals sine x is cos x. And if we have a function y equals cosine of x, and we take the derivative of that, we get y prime equals negative sine x. Okay? So sine x and cosine x are kind of derivatives of each other, with the cos x, the derivative of cos x, being negative. Okay? So these guys are fairly straightforward to remember here. And if you want to see kind of some justification for this, I mean, we can look at the graphs of sine x up above, cos x down below, and if we just go to sine x here and we say, pick a point right here, we draw our tangent. The slope of the tangent here is 0, and if we go down and look at what the value of cos x is, well, value of cos x is equal to 0. If we come to another point, and if we go right to x equals 0 here, we draw our tangent. Tangent has pretty much a slope of about 1, which, hey, lo and behold, is the value of our cosine here. And as we go from 0 here to pi over 2, the slope of our tangent is getting progressively smaller. Okay? Just like in our cosine function, the value of cos x is getting smaller and smaller and smaller till it's down to 0. Okay? And we can do the same sort of thing with cos x. Everywhere we drew the tangent on the cos x function would be the value of the sine function, except it has to be negative. Okay? So let's just take a look at a couple of examples of applying these two rules that we've just established here. So actually, I got 4 examples here. First one is pretty straightforward. Y equals sine 2x. Okay? And we just want to take the derivative here. So already we're having to use chain rule, because this isn't just a straightforward sine x. This is y equals sine of another function, g at x, where g at x is just 2 times x. So our derivative is going to be, well, we've got to do the derivative of the sine x. So derivative of sine x is cos x. So it's going to be cos evaluated at that function, g at x, times the derivative of g at x. So this is just our chain rule here. So we can do this specifically for sine 2x. We've already said we're going to have derivative of sine is cos. We've got to have the 2x. It's got to be cos 2x because we're evaluating this at that same inner function there. And then we're multiplying it by the derivative of that function that is inside. So the derivative of 2x is just going to be 2. And usually we reorganize these so that the coefficients are out in front. So this is going to be 2 cos 2x. Our second example here, move this one down out of the way. Y equals cosine squared x. Chain rule again. What you want to think of when you see a cos squared or a sine squared is, remember that this means cos x squared. Okay? So that makes it a little bit clearer as to how we have to apply the chain rule here. How are we going to apply the chain rule to get this derivative? what do we have to do first with that exponent 2? Yeah, we've got to bring it down. So it's going to be 2. What's in the bracket stays the same, cos x. Now we would have an exponent 1 here, so we don't even have to bother writing it. But then what do we have to multiply this by? Sine x, because it's the... Yeah, we have to multiply by the derivative of the cos x, derivative of that function that's inside, which is negative sine x. So cleaning this up a bit, we get negative 2 cos x sine x. Okay. Okay. Next example here. All right. Example 3 here, y equals sine of 4x squared times cosine of 3x. So in this case, we're going to have to use the product rule because we have two functions of x that are multiplied by each other. And for each of these functions, the sine and the cosine, we're going to have to use chain rule to get the individual derivatives. So just to make this clear, we've got u and v, and we're going to do our standard u prime times v plus u v primed. So what is our derivative of u going to be if u is sine 4x squared? Yes. Derivative of sine is cosine, evaluated at that same inner function, and then multiply by the derivative of what's inside, which is 8x. So there's our u primed, and we have to multiply that by cos 3x. So that's our u primed, and this is v. To this, we're going to have to add our u, which is sine 4x squared, which is our original u, times the derivative of that v function. So what is the derivative of cos 3x going to be? Well, let's see. Derivative of cosine is going to be negative sine. Keep the argument the same, so it's a negative sine 3x, and then multiply by the derivative of what's inside the brackets, times 3. And that's v primed. Okay, and now we would look, try to clean this up a bit. We would look for things that we could factor out. We've got cos and cos in our first term and sine in our second term. So we can't really simplify this too much, but I'm just going to write it as 8x cos 4x squared cos 3x minus 3, because we've got the minus on the sign, we've got the 3 as our coefficient, sine of 4x squared sine 3x. All right, last one here. We've got y equals ln of cos squared 3x. So we're working a logarithmic function in here. What do we want to do? There's a way of simplifying this a little bit before we go ahead and do our derivative. It makes it a little bit easier. Austin? Now, you're already doing the derivative, even before we do the derivative. Yeah. We can think of this as ln of cos 3x squared. Okay? Always think of these cos squareds and sine squared as cos something all squared. Now we can apply our laws of logarithms to bring that 2 down out front. So this is 2 ln cos 3x. Okay. Now how does that help us? Because if we look at the original one, we've got 3 functions. We've got a bunch of functions. How many functions do we have nested here? We've got the ln function, we've got the squared function, we've got the cos function, and then we've got the 3x function. So that's 4 functions nested one inside each other. By rearranging that, though, we take care of one of those functions. Now we don't have that squared in there, and we just have to do the derivative of ln cos 3x. So let's do that. We're going to have this whole thing multiplied by 2. Let's do the derivative of the ln function first. Start on the outside, work our way in. Austin, you were already onto the derivative of the ln, so what's it going to be? So what is the derivative of that inside function then? This whole thing is the inside function. So cos 3x is the inside. So what's the derivative of cos 3x? Exactly. Then we have to multiply by the derivative of the function which is inside there, which is where the 3 comes in. Okay. So we can clean this up a bit. We get negative 6 sine 3x over cos 3x. Now, if we're really ambitious, we can simplify this a little bit further. Because we have sine 3x over cos 3x. Sine over cos is tangent. Yeah. So this is negative 6 tan 3x. Yeah, that's as simple as it gets. So weird. We started with a ln, and we ended up with tan somehow. Weird. Weird. Okay. All right, so that is those two derivative rules combined using the chain rule and the product rule with the other derivative rules we already knew. So I got 2 questions here that are sort of the standard applications that we've been asking all along. Here's the first one. Oh, before we even do that, things to remember when you're working with trig functions. Calculator in radian mode. Sometimes we do these questions in radians, sometimes we do them in degrees. Okay? Every time you see a pi for one of your angles, you know that we're working in radian mode. Okay? If it doesn't specify, kind of assume that we're working with radians here. You got to remember these special triangles, 1, 1, root 2, 1, 2, root 3 for our pi over 4, our pi over 3, and our pi over 6 angles there, if it asks for an exact answer. There's the cast rule that you started working with back in grade 11 that tells you the sign of each of these trig functions in each of the 4 quadrants. Okay? And you have to remember that a lot of times you're working with your reference angles, and you have to apply the cast rule to figure out what the sign of your answer is going to be. Okay? So just keep all of those things in mind as we go through these examples here. First example. Find the equation of the tangent line to the curve y equals sine x minus cos x squared at the point x equals 5 pi over 4. Okay, so this is a standard question. I mean, we've asked you a million times how to find the equation of a tangent line. We're just giving you a trig function now. So what is our first step? You're going to do the question? All right. Yeah, so let's do our derivative first. Okay. Let's see, sine x minus cos x all squared, so we'll bring down the 2. We'll have sine x minus cos x inside the brackets, and then we need to multiply this by the derivative of sine x minus cos x. So we can do this term by term. Derivative of sine x is cos x. Derivative of minus cos x, well, let's see, we can subtract the derivative of cos x. Derivative of cos x, though, is minus sine x And so we get cos x minus sine x, or cos x plus sine x. So sine x minus cos x times cos x plus sine x. Now, at this point, I'm going to multiply this out. I'm going to expand it because I know that because I have the same two terms here, sine x, cos x, one positive, one negative, I'm going to get some terms that cancel out. So this is going to work out to be 2 sine x cos x, but I'm going to have a minus sine x cos x that cancel. So I'll end up with sine squared x minus cos squared x after I do that expansion. If it was a plus sign in the middle, it would be equal to 1. But it's a minus sign. Alas. So we've got our derivative here. What do we want to do with our derivative now that we have it? So we sub in x equals 5 pi over 4. So what I would do is I would evaluate sine 5 pi over 4 and cosine 5 pi over 4, okay, because they both appear in my expression here, and then evaluate what the whole derivative is going to be equal to. So 5 pi over 4. What does this angle even look like? What quadrant is it in? It's got to be in the third quadrant, because 4 pi over 4 would be just pi, which would be 180. So it's got to be down in this quadrant here. And our related angle, or our reference angle, in there is pi over 4. So if we want to do this exactly, we've got to use our special triangle for pi over 4, which is our 1, 1, root 2 triangle. And he draws a square root in there. Let's just do pi over 4, 1, 1, root 2. And that's a horrible looking triangle. I'll put an arrow. Pi over 4. So if we're doing sine, we have opposite over hypotenuse. So 1 over root 2. But we're in third quadrant, so we apply our cast rule, which tells us that only tangent is positive. So this has got to be negative 1 over root 2. Cosine, we've got adjacent over hypotenuse, which is again 1 over root 2. Apply the cast rule, only tangent is positive, so this is going to be negative as well. So we've got sine 5 pi over 4, we've got cosine 5 pi over 4. Let's work out what the value is of our derivative. It's going to be 2 negative 1 over root 2 squared minus negative 1 over root 2 squared but since sine and cosine are exactly the same, those are going to cancel out, and our derivative is just 0. So what does this tell us about our line here, our tangent line? It's horizontal, exactly. So where do we go from here? We want to get the equation y equals mx plus b. We know that we can already sub in 0 for our slope. What we still need is x and y. We know that x is 5 pi over 4. Y is going to be, well, let's go back to our original function here. Original function was sine x minus cos x, so it's going to be sine 5 pi over 4 minus cos 5 pi over 4, and this whole thing was squared. We already know what sine and cos of 5 pi over 4 are because we evaluated them up here. So we can just sub in those values there. We get negative 1 over root 2 for each of these. And we're going to square this. And what do we get here? 0 again. So what we get is 0 equals 0, 5 pi over 4, plus b. B equals 0. So y equals 0. So our tangent is just the x-axis for this one. All right, so standard type of question here. The other kind of question we like asking you. Find the local maxima and minima of this curve, y equals sine x plus cos 2x over some interval. What's our first step here? Derivative. So our derivative, we can do this term by term. Derivative of sine x is cos x. Derivative of cos 2x is going to be, sorry, not cos x, but negative sine 2x times 2. Where I'll put the 2x in brackets there. Okay. And so the equation we need to solve here is, we set it equal to 0. 0 is going to be cos x minus 2 sine 2x. Now what's tricky about solving this the way it currently is formulated? Convert what over to cos? Yeah. Yeah. Yeah, the problem we have here is that this is cos x and this is sine of 2x. Okay, so these trig functions don't have the same argument. So what do we do in these cases? Well, we have to apply an identity to get it so that both of these are the same. So the identity that we're going to apply here looks like this. Okay, this is going to be 2. Sine 2x is 2 cos x sine x. So there's our identity. Let's see. So we've got 4 cos x sine x. Now what should we do? Yeah, we can factor out the cosine, which gives us 1 minus 4 sine x. So this gives us two equations that we can solve. We can solve cos x equals 0, and if we rearrange the stuff in the square brackets, we get sine x equals 1/4. These are our two things to solve. Cos x equals 0 is pretty straightforward, because we can just think about what the graph of cos x looks like. Where does it reach 0? It reaches 0 at pi over 2 and 3 pi over 2. I know that I have to work in radians because in my original question, the domain was given to me in radians. What about this one over here? Sine x equals 1/4. This is one that I'm going to have to solve. Go ahead. Yeah, I've got to do this one numerically. Just plug this into my calculator. Inverse sine of 1/4. Now, I punch this into my calculator, and I get 0.253. Is that the only solution? Brody's shaking his head. What do we have to consider here? Yeah, the domain, yeah, which goes 0 to 2 pi. So we have to think about, your calculator is always going to give you, if this is positive, it's always going to give you the quadrant 1 solution. So this is the solution that we have right now. Where else can the sign of x be positive? Well, let's see. Cast rule tells us, C-A-S-T, that we're also going to have a quadrant 2 solution. So what's our quadrant 2 solution? Well, this angle in here will be the 0.253. So x is going to be pi minus 0.253. Which gets us 2.889. So we've got our solutions here, 4 of them. 2 of them we have exact, 2 of them we got numerically. Well, we go back to the original question here, and we see what it's asking us. Find the local maxima and minima of this curve. So we need to figure out whether these critical numbers represent local maxima or local minima, and find the coordinates, or the y values. What can we use to figure out if these are maxima or minima? The second derivative test. So we are going to use second derivative test. So we need our second derivative. So I'm going to go back to our first derivative here, and if I just scroll up here, I think where we want to take the second derivative is after we've applied our identity, but before we've started factoring. Okay, so I'm going to start at this point right here where we have cos x minus 4 sine x cos x. And I'm going to do the derivative here. So our first term is pretty straightforward. Derivative of cos x is negative sine x. Then we can subtract 4 times the derivative of sine x cos x. Sine x times cos x. We've got to use product rule here. So derivative of sine x is cos x times cos x plus derivative of, we've got sine x, our original u function, times derivative of cos x, which is negative sine x. So we can clean this up a bit. Negative sine x minus 4 cos squared x. Sine x times sine x gives us negative sine x squared times negative 4 gives us plus 4 sine squared x. And this is what we have to evaluate for each of our critical numbers. So probably what you would do is just do this numerically. Punch these things into your calculator. So if x is pi over 2, figure out what y double primed is. And I've done this. Y double primed works out to be 3. Okay? So if y double primed is 3, this is positive, which means we have a local minimum. Okay? And we can work out what our y value is from our original function. And you work that out, and you get a y value of 0. Okay? And we want to do the same thing for each of our points here. So x is 3 pi over 2. We get y double primed is 5. So we have another local minimum. And our y value there is -2. Then those are our two exact solutions. Then we've got to do it for our two approximate solutions. So those were 0.253. We get y double primed is equal to -3.7. And it doesn't matter how accurately I get this second derivative, because I'm only really interested in the sign. So my sign here is negative, so this is going to be a local maximum. And I go ahead and I work out my y value is 1.125. Got 1 point left to go here. It is 2.889. My second derivative works out to be -3.7 again. So I've got another local maximum, and my y value works out to be the same thing. So I could sort of sum all this up by saying, therefore, we have a local min at pi over 2, 0, and 3 pi over 2, -2. And we have a local max, two local maxima at, and then just put in our approximate values here. 0.253, 1.125, and 2.889, 1.125. And I don't have room for the 5. And that's what they were asking us for, the local max and the local min. Okay, so we're done.